Think about this. We have this array, we break it, we say that we are going to break it down into two separate components, but in essence, we are not copying the array into two separate components, right? We are just saying, take this array, just work on this half of that array, and the other person works on this half of that array, right? So once those halves are sorted, it is essentially the same original array, where part of that array is sorted and the other part of that array is sorted. Right. So once we have this, you can think of it like 2, 4, 5, 7 has been sorted out. Right. These are in sorted order. And this half of your array, 1, 2, 3, 6 is also sorted out. But now we need to merge them together into a single array. Now, merging them together means that 1 goes here, then comes 2, then comes 2, then comes 3, 4, 5, 6, 7, and so on. Right. So there are algorithms that do it in place, but we will first talk about this merge process, and then we will talk about in place merging procedures. But it's essentially what people usually do is we copy the first half of this array into a new array called left array. We copy the second half of this array into a new array called the right array. Now that we have this, we are now ready to compare the first element of L and the first element of R. So we compare 2 and 1. 1 is saved as the smallest element there. Then we compare 2 and 2. So 2 is saved as the first element, second element there. Then we are comparing 2 and 3. Then essentially 2 goes there as the next element there. Then we are comparing. So as we are comparing, we are basically moving forward. It could be that one array is exhausted before the other array, but essentially because we don't know if they are completely interleaved, more often than not, they're not going to be interleaved. You can imagine an array where it is 1, 2, 3, 4 as the first array and 10, 11, 12, 13 as the second array. When combining them, we can just merge them together, but essentially we need to go through each element every time. So we get 1, 2, 2, 3. Once we combine them together, essentially step by step at each point in time until we exhaust one array or we exhaust both of those arrays. And once we have exhausted both of those arrays, we get our final sub sorted array, that is 1, 2, 2, 3, 4, 5, 6, 7. Any questions about this? Sorry for the police siren. Any questions? No questions? Okay, tell me if there are no questions, if you guys understand that clearly that much. So in this situation, let's say that my sub array size is n. Can someone tell me how much extra memory do I require in order to merge two arrays of size n by 2 and n by 2? So what I'm asking is, I have two subarrays of size n by 2 and n by 2. What is the extra memory that I require? How many bytes of memory do I require, or in terms of n, in order to merge these two arrays? Or do I even require extra memory? Can I just deal with without requiring any memory? Swapping. I see n, I see 2n, I see 2, and I see swapping. Give me at least a tiebreaker, someone. In addition to A, exactly, extra memory apart from the array itself. N, okay. So essentially it is going to be a space complexity of n. So we need an extra complexity of space, that is an extra memory requirement of n size. Because we are not doing this, so because we are doing this with the help of extra two arrays. If we wanted to, we would have required that we somehow merge these two arrays in place. We call that as in place sorting. So this is not in place merging, but there are algorithms that are called in place merging, where we merge those two components together into a larger array in place, so without requiring any memory. And that is a complicated problem that we are not going to look into today.
Do those algorithms run at nlogn as well?
No, the time complexity changes a lot. That is a good catch. Since we are increasing the memory requirement of this merge sort by requiring more than the array size, that is essentially another segment of our array. That is the space-time trade-off complexity, right? Space-time complexity trade-off. If you add more space, you will require less time. If you require more time, then you can do it without much space.
Oh, so there's a trade-off typically when you're doing these kinds of algorithms?
Just, I mean, think about it. Let's say that I have these numbers, right? Let's say that I have these numbers, that is 5, 2, 9, 10, 1, right? These are unsorted numbers, and I'm guaranteed that my array will only have numbers in this range, and it will going to be unique numbers, blah, blah, blah. And I have these numbers. Now, what is the best that I can do in order to sort these numbers? Anyone? Can I do it in big O of n? Is the best that I can do is big O of n cubed? Well, I have bubble sort, so I can do it in squared. Can I do it better?
Yeah.
N log n, as we just talked about. Can we do this better?
Counting sorts ON, correct?
Counting sort is what? In log n?
I thought, isn't counting sort ON?
Yes, exactly. Counting sort and radix sort and those algorithms are in ON. So what they do is, say that I have 20 numbers or whatever, right? What they do is, so my number range is provided, let's say, it's going to be from, the numbers are going to be from 1 to 10. So what they usually do is they just assign the number to the correct, to the required index. So let's say I have these indices, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? These are my indices. So now I have the number 5. So I just say, okay, 5 has the number. So I just place a 1 there. For this, I place a 1 there. For 9, I place, I did it wrong. It should be here. Oh, come on. Indices start at 10, 1 here. Okay. So for 2, I have a 1 here. For 5, I have a 1 here. For 9, I have a 1 here. For 10, I have a 1 here. And for 1, I have a 1 here. Right. So now, or let's say the remainder of those values are not there. But if you think about it, I can just now read this array in order. And whenever I see a 1 there, I can then just print out that particular index. That would basically mean that I have a time complexity of big O of n, or 2n, but essentially big O of n.
But this is only when I'm aware of the range.
Yes, this is only when, now just theoretically talk about infinite space is being provided to you so that you are allowed to have infinite numbers. So in that situation, you have that. But as Brian says, that is a lot of wasted space, right? I am now potentially have a very sparse memory allocation where most of those values do not have any actual usage. Now, Vamsi, so Vamsi says that what if I have duplicate values? So if I have duplicate values here, let's say I have another 5, I just make it 2. Yep. And I just print the number twice, but that is still within n, right? Okay. So there is a space-time complexity trade-off across algorithms. And if you want to do in-place sorting, in-place merging, God knows I have wasted a lot of time on in-place merging, but you can just look at it if you want. But in general, merge sort does not care about that. Merge sort assumes that you're going to use this merge procedure that is essentially taking a copy of those and merging them together. Okay, now moving on. Okay, so that was the merge sort algorithm, but given this algorithm, we have to do two things. First thing is find the time complexity, but the other thing would be, can I prove that this particular algorithm would work across all cases? Right, so for that, we need to do an inductive hypothesis. The first would be figure out if the base case works. Then assume that your sub-problems, and that is the inductive process, assume that your sub-problems are correct and correctly analyzed. Then the combining process would be, if the inductive process is correct, then once I combine the entire thing, the algorithm should give you the correct answer for the original problem. So in case of merge sort, the base case is if n equals to 1, if I just have the one element, then merge sort works fine, right? Because we have this base case here, because a single element is always sorted. So the base case is done. Now the inductive hypothesis, that is, assume that once you break your array down into two separate components, a to n half and n half to n, then you assume that those two sub arrays are sorted. Well, they are going to be sorted. And then finally the step is, you're assuming that once you merge them together, merge two separate smaller subproblems together, after you merge them, you will get the final sorted answer. Well, we just check the merge procedure and that works. And we just made the hypothesis that once I break down the array and merge them together, then it is a correct algorithm. So that is what we mean when we say correctness of a particular algorithm. Okay. Okay, so now comes the question, given that I have these recursive formulations, how do I figure out what is my recurrence formulation of my particular algorithm? So I have this algorithm that does merge sort. How do I write this particular algorithm in terms of my recurrence relations? So we had our merge sort algorithm that takes in the entire array, right? So the total complexity of this function should be T of n. Now our duty is to figure out what T of n is. So in this case, we will break down the three things: the divide part, the combine part, and the conquer part, right? So essentially, let's just first take the base case. Now the base case just checks if n equals to 1, then I'm done. That takes theta of 1. Does everyone agree that this particular step does not take more than, takes basically a constant time? Yes. Anybody else? Okay. Now we have this recursively sort the two halves. Now this does not have a time complexity, but this is essentially the combined time complexity of sorting the two halves, right? I'm going to sort the first half and I'm going to sort the second half, and then I will do things with it, but essentially I need to sort the two halves. So if sorting an entire array takes T of n time, then sorting half an array should take T n by 2 time, and I'm doing it twice. So that means the entire time for sorting these two subhalves would be 2 times T n by 2. Okay, and now we need to merge these two halves together to get a final sorted list. And that is going to be some complexity function. Let's call it Fn for now. Okay. Okay. So all of these three things together make up your time complexity in the recurrence formulation. So let's see what that looks like. So the divide part is trivial. We are just figuring out the middle part of each array and then calling it again. So dividing your array basically requires theta 1 time. Calling and sorting the individual halves require 2 times T by n by T of n by 2 time, right? Okay. So these are your subproblems, where each of these are your subproblem size. And then we have f of n, that is the time complexity for combining those two arrays together. So for the base case, we know that our time complexity is constant, but